Welcome to the final video on the chain rule. We're going to talk about some interesting applications of the chain rule where you actually do have to use it. So we got a store, and the store is selling ties for $12 each. And every day they sell about X ties. The revenue is given by this revenue equation. And if the daily sales are rising by 4 ties every day, how fast does the revenue grow over time? Right? If the revenue, right, this makes sense that this is the revenue, right? Revenue is just the price times how many you're selling. So they're selling for $12 each, and we're selling X ties. So that revenue equation should make sense. All right. So here we go. What do we want to know, right? We want to know how fast does the revenue grow over time? We want the rate of change of the revenue with respect to time. Well, the chain rule says, right, that we can write this as dr dx dt. Right? Because we know r and we know how it relates to x. And we know how x changes over time as well, right? This right here, this is how does x change over time? Well, look at this. Look at this thing over here. The sales, which again is x, rises by 4 ties every day. That is our dx dt. So let's look at this. The r dx, the derivative of r with respect to x, is just 12. Derivative of x with respect to t, that's the rate of change. How does x change? How does the number of sales change over time? Well, it's growing by 4. It's growing, so it's a positive 4. What we have here is 48. What are our units? Units are always going to be the units of revenue, which is dollars, divided by the units on the bottom, which is time. It's going to be $48 per day. Every day we're getting $48 more than the day before. All right. And again, it doesn't matter. Notice we don't even know how much our daily revenue is. I don't know the revenue I'm making today. I don't know the revenue I'm making tomorrow. I do know I'm making 48 extra dollars though. Store doesn't actually need to give you the other information. Oh, I added an extra page here. It's okay. Let's look at example 9, the last example. So we have some manufacturer and they have a product following this demand function. Remember, demand function shows the relationship between the price P that I want to sell at and how many things X I can sell. So the more things I want to sell, as X gets bigger, right, the price is going to be smaller. If I want to sell more things, I got to charge less. Okay. Anyway, how fast does the revenue grow at a production level of 6,000 if the company is increasing production by 200 every day? We're asking for a similar thing. How fast does the revenue grow at a production level of 6,000? Okay. So we're going to want to know what is the rate of change of our revenue over time. Unfortunately, we don't even have a revenue function here, right? But don't worry, this is 2.7's time to shine. 2.7 was just last week. And so we remember that the revenue for a product is how many things are we selling and what price are we selling them at, just like the last example. And P, again, is just 86 minus 0.002x. We can rewrite that a little bit, right? That's 86x minus 0.002x squared. So I can find the derivative with respect to x. I can find r prime of x, no problem. Right? The derivative of r with respect to x, that's easy. But as I've written it now, this is not a true statement. These are different derivatives. So we make it true with that chain rule. Multiply by dx dt. And again, the way to remember that this works, right, is that the dx's cancel, dr dt. So we'll look at the derivative of the revenue function with respect to x. That's going to just be 86 minus 0.004x. That is the derivative of the revenue function with respect to x. It is the marginal revenue, the additional revenue from increasing production by 1. We also multiply by dx dt. Well, what is dx dt? Dx dt is the rate of change of x with respect to t. How production changes over time. Well, the production is getting increased by 200 every day. How's the production changing over time? It's 200. All right, so that's dx dt. And we're getting pretty close. We could multiply this out. 200 times 86, oh my word, is 172 with 2 extra zeros. Minus, yeah, this one's not happening in the head. All right, it could, but it would take a little bit more time. I don't want to keep you guys waiting. 0.8. Wait, that's not hard at all. Never mind. So are we done? This is the rate of change of the revenue over time. Isn't that what it wanted us to ask? Well, hold up. How fast does the revenue grow at a production level of 6,000? So it specifically wants to know when x is 6,000. Okay, so when x equals 6,000, and I know you can't see that word. Right, dr dt is going to be 17,200 minus 0.8 times 6,000, which comes out to some number. I can't type on my keyboard with this little glove thing. I have this so it doesn't like get my fingers all over the tablet. 12,400. And again, for units, it's always going to be, what are the units at the top? What's the units of revenue? Units of revenue? Dollars. Divided by the units of time. Units of time is days. Days doesn't start with H. Nice try, Jason. So our revenue is growing by $12,400 every day. I like the sound of that. All right. Who knows how our costs are growing though, right? Profit's going to be the difference between revenue and cost. So maybe the costs are also growing a lot. But either way, here we go. That's how you do these problems. Good luck.